So the last couple of videos I've been implementing this toy linker, and today we can finally get to the reason I am implementing this toy linker. Namely, for the last couple of years at this point, like the last 2 years, I've been trying to document the PDB format. And the linker is supposed to be, in the end, an example for how to write out one of these PDB files. And so today we can finally get to it. We can finally try to take all of these object files, which are compiled to contain code view debug information, and try to write out a correct PDB file. So the PDB file format is awful. It is way too complicated for what it does. There's no documentation on it. There's some cryptic source code that Microsoft published, said they would keep up to date somewhere here. And at this point it's archived, and well, but they did leave us the source code for one of the core libraries, MSPDB core or whatever. And yeah, so from that mostly, and some other libraries, some other sources of documentation like the LLVM implementation and Wikipedia articles and some random implementation, I was sort of pieced together how this format works. I've implemented it like 5 years ago in my compiler, but the implementation I have there is incomplete, kind of horrible. I was not really sure what I was doing. And so, like, again, 2 years ago, I've decided enough is enough. Someone has to document this format, and I guess I'm going to be the one. All right. And so today, yeah, I want to get not far. I want to be able to write a sort of empty PDB file, and I want to write the RSDS debug section, so the code view debug section, inside of the exe that links to this empty PDB. Then hopefully in future videos we can attack like the type information that's supposed to be in the PDB, and the line information and the symbol information and so on. Okay. So to give a little bit of an overview how the PDB format works, there are sort of two things to it. There's the multi-stream file format, and then the layout of the PDB itself, and code view, which is the actual debugging format. So we not really have to care about code view because, at least for now, we might have to in the end, but for now we only care about the PDB format and the multi-stream file format. And so the multi-stream file format is sort of a file within a file system within a file, more or less. It just takes a bunch of so-called streams and, well, has them in non-contiguous pages, and any code that deals with PDBs is supposed to think of these streams as contiguous. And the good thing here is I've already implemented code for this, so we don't have to care about the multi-stream file format. We can just assume we only have to provide the PDB streams, and then my code that I've already written can write out a correct for a file in the multi-stream file format. And so we only have to care about the PDB stream layout. And so the PDB consists of multiple different streams, and each of these different streams has a layout associated with it. And so there are sort of 4 fixed streams. So this is all about the MSF file. And then there's the stream table stream, which is at stream index 0, but that one is handled by the overall MSF file, format. And so we only care about the PDB format. And so here's a table of all of the streams. There's the PDB information stream, which is as file index 1, which this is the one that we care about today. Everything else we'll do in future streams, videos, hopefully. There's the TPI stream, which is type information, DBI stream, which mostly contains links to other of these streams, so like module symbol streams, and so on. Then, well, IPI stream, which is like ID records. I don't really know what they do, but they are in there. And hash streams for TPI and IPI. Then the rest, we might have to care about the dash name streams today, but I'm not even sure we have to do that. Okay, so far for that. And I've already done like the tiniest amount, namely I have altered the C file, test.c file, to use actually the MS-PDB core library that is, well, which is the one that they published here. So we can look at the include file, and it is a DLL, so it exports some functions. And yeah, some of these functions I could call to write out a minimal PDB file, which is valid according to MS-PDB core. So yeah, the way I do this is just I found out the type definition for all of these, then I load library A, MS-PDB core, I open, I get proc address on all of these functions, and so I open a file, then I commit, which is committing changes to a file. This is how this format works. And then I just close it. And that writes out this minimal.pdb. So I have this right here. Minimal.pdb. It's 11 kilobytes. And there are two tools that we are also going to use. One is the Microsoft tool, which in this repository, they just shipped an executable, namely this cvdump.exe, which tells us, well, it dumps PDBs. So if you do cvdump, you can see most of these, it tries to open particular streams, but they don't open because they're empty or whatever. And yeah, it doesn't tell us much because this is an empty PDB. And then I've also written one of these tools myself, validate, which tries to check as much about the PDB format as possible, which is also one of the tools that is going to be in the PDB documentation thing. Okay. If I do that, well, it tells us it has a PDB information stream, which is the stream at stream index 1, which contains this information. Then there is the named stream table is apparently empty. This is the only feature flag in it. And then all of the other streams are empty. So the 4 fixed streams. Maybe we'll get a little bit further than this today, but I'm not sure. Okay, so let's get started. And so the way I'm going to do this is to actually create a new file. So let's call it write PDB, maybe. And for now, this doesn't actually take any arguments because later on, it will take all of the different compilation units, or there may be information about them. But for now, the minimal PDB doesn't have anything to do with the executable. So int for like an error code maybe, Let's do void for now, actually. Call it write PDB. And again, I've told you we needed this other code that I've already written, which is in the PDB thingy here. We have way too much stuff in there, but it should be called, or is it not in here? MSF, yeah. So it should be this code right here. And so let's copy that file from here. Kill this. And Explorer. Open the Explorer here. Put in this MSF file and then open it. And this has a write MSF function. Okay. Then what I will do, currently the compile command in my config.gpe, I think it's just hlc linker.c, but now we also need these other two files, so msf.c and the write pdb.c. Okay, and let's try to compile that and then see if there are any errors. So load file redefinition. Yeah, because I don't care that this is loading files, this is test code. So let's if 0 the test code. Actually, let's just delete the test code. And then it links. Okay, and so the way to use this is we call write MSF, we give it a file name, we give it streams, which it's supposed to write into this MSF format, and the amount of streams. And in write PDB, I'm just going to, for now, set these up. So let's pick a file name. Our executable is currently called a.exe, so the file name actually let's call that by value, so write msf, and we have a file name, let's call it a.pdb, and the streams and then the amount of streams. And so we need 4 streams for now, because there are 4 fixed streams in the PDB format that's always exist. We look into this. So this is just the same, that will be online, but a little bit more updated and local. There's fixed stream 1, which is the PDB information stream, fixed stream 2, fixed stream 3, and fixed stream 4, which are TPI, DBI, IPI. And so these 3 were empty in the minimal file that we looked at, and this guy was filled out. So let's do struct, I think it's MSF stream, yeah. Streams of 4 are 0 initialized, and then we pass in the streams and this array count of streams. And then in the linker, we go to the end of the linking file, which is, I think, is just main. Yeah, So we write a.exe. We just call write PDB for now. Then that compiled, and if I run the linker now, the way we have been compiling or linking the broke.ce game, not broke. Just cd broke ce, and then link. Currently still calls the linker. Okay. New link.bat, remove the compiler. The debugger. I said linker first, then compiler. It's the debugger. Okay. Link. Okay, and this apparently still has some debug spam, but it's writing some stuff. And it should be, I've tested this enough, a valid MSF file. Okay, so what we have now here is a dear a.pdb. Yeah. So far, so good. Obviously, this PDB, a.pdb isn't actually a PDB yet, but it almost sort of is. It adheres to the MSF format, but we need to fill out this one entry to actually make it a PDB. But the more important part maybe is to link up the PDB and the executable together. And so the way this works is, can I search in here? Maybe not. Is the RSDS debug entry. So in the section how our PDB is used, essentially if we dump in /headers on a test program, it gives us a debug directories thing. And each of these debug directories has some format in its own, and the one that we care about of type CV or RSDS starts out with RSDS, so I'm calling it RSDS, contains the signature, then the grid of the PDB, the age of the PDB, and then the full path of the PDB. So looking at this, it says RSDS, some grid, the age is 3 apparently for this one, and then the full path of the PDB. And so the way why there's a grid and an age, so they generate one of these grids to link them up. Then, but if you link incrementally, it doesn't regenerate the grid, but just increments the age. So that's why there's both a grid and an age. But okay, so let's first of all go into the linker and add one of these RSDS debug entries to link up the PDB and the exe through this debug entry and this full path, essentially. And I'm going to do that again in the RData section. I'm going to put this entry here, allocate an RData section if it does not already exist, and we need space for DLL imports. Also need space for the RSDS debug entry. Okay. So here the way this works is I iterate all of the section and try to find the RData section. If I find it, then I take that one, and otherwise I create a new one. And then here I have this DLL import information size, which I add to the end of the RData section. Okay, but now I also want to add the size of the RSDS debug directory. So let's call it I don't think I need this afterwards, so let's just go here, and so I call it RSDS debug directory entry size. And this is, well, 4 plus 16 plus 4 plus the length of the path, and I'm currently going with just a.pdb, and maybe that'll work, maybe we need the full path. Or do I just specify the full path? Yeah, let's just specify the full path, and that might be wrong the way this works, but it's fine. So size of really hacky for now. This would be here. So this path a.pdb. And let's put some comments here. RSDS grid and age. So, but we don't only need a RSDS debug directory entry, because I think the way this works, if we look in the PDE spec, there's multiple, like the debug directory consists of multiple debug directory entries. Debug directory. So yeah, the debug directory, image only. Let's get this to here where I can read it. Image files contain an optional debug directory which indicates what form of debug information is present, where it is. This directory consists of an array of debug directory entries whose location and size indicate in the image optional, which are indicated in the image optional header. Yeah, so this is one of these directories. Each debug directory entry identifies the location and size of a block of debug information. So this RSDS thing that I was talking about is a block of debug information, apparently. The specified RVA can be 0 if the debug information is not covered by a section header. Okay, it's not what we have. Okay, the debug directory entry has the following form. Characteristics must be 0, time date stamp, major version, minor version, type, size of raw data, size of data, address of raw data, when loaded, so this is an RVA, and pointer to raw data, which is not an RVA. So let's maybe get this to here, which ruined everything, of course. Get this one to the other side. And so we also need one of these. So this is, I guess, US64. Let's get this cable out of the way. Debug directory entry size, and this is 28. And then this is the RSDS. What did it call it? Called it block of debug data, debug information. Let's call it just debug information. And then I'm going, instead of just having this DLL import information size here, I'm going to go RData size. And the RData size is this plus debug directory entry size plus the RSDS debug information size. Okay. So then later on, first of all, we need to know the offset of this. So here I have the import lookup table RData start. Oh, which I set here. Sure. So what I need is a debug directory RData start. I guess also starts out at 0, but then here we set it to kind of want to turn this around. Instead of getting this later, I get this here. And here I align it. Sure, I can do that. Okay. So we align the size. And then we say that the debug directory, no, the import lookup table RData start is the current value. Then we add the DLL information size and set the debug directory RData start. I guess these also don't have to be aligned, so let's align them again. And then set the RData start finally to the size of raw data. Then re-add these two. To make it a little bit more obvious what belongs to what, I am going to here make a scope like this, let's say. DLL import size. maybe let's say calculate. And then here, calculate debug information size. Okay, very nice. So now we have allocated that and we know where it is. So where we are interested in this import table, import lookup table rdata start. Like here, right in the DLL import information, we are also going to have a section which is like right in the debug data. Okay. And yeah, so the way we calculate this here is we get the relative virtual address and the information base out by just adding the offset we have calculated to the relative virtual address and pointer to raw data respectively of the RData section. This is now not DLL import information, but let's say debug data. Debug data. Okay, and then also not this import lookup table rdata start, but the other guy, which I have forgot again, debug directory rdata start. Okay. And so the first thing that the debug directory points to is this debug directory entry. So struct debug directory entry is just void star debug database. Sounds like database, but whatever. And it has a characteristics. Let's unmark this so we can read it better. Characteristics. It is not spelled correctly, is it? Doesn't complain. The time date stamp, a minor version and a major version. A type, a size of data, and a address of raw data, which this address of raw data I am going to call data RVA because that's what it is. And then pointer to raw data. Okay, so the characteristics must be 0. The time date stamp I think we can be let be 0. No one cares about that. Then the major version and the minor version. And so here I want to look at the CD. What? Actually, I didn't have that in there. I had it in this information. So does this tell me anything about a major or minor version? There's the time, the type, the size, the RVA, and the pointer. But nothing about a version. Do I have to... Let's leave him 0 and see if that works, I guess. I guess maybe it wouldn't be too hard to find. Like way too long, but I figured out the major version and minor version are just 0. Okay. So we can fill the structure out. The characteristics, like this already told us. Let's put this here and it will screw up everything again. So debug directory, go here. Characteristics must be 0. The debug directory entry time date stamp. It's probably just a time date stamp, so we're going to call time now. The time date was this created. Yeah, it's probably that. Otherwise, it probably also won't care about it. As I figured out after way too long, these major and minor versions are also just 0. The type is code view, so 2. Type is yes, and then the size of raw data I guess we can recalculate, or we can take the same thing we already had up here, so this right here. But I think I'm just going to recalculate it for now. The address of raw data is what we calculated here, plus the size of one of these debug directory entries, because we let it follow exactly after the debug directory entry. So the data RVA is the debug data relative virtual address plus the size of this debug directory entry. And the debug directory entry pointer to raw data is again the same thing we have here, plus the size of one of these debug directory entries. Okay. These are all the fields filled out of that. And so now we get to the RSDS. Do I still have that somewhere? No. Oh. Okay, here. But we can recopy it. So one of these guys. Directory, and this is U32 RSDS pointer to raw data. just pulling that out and adding the image base to the pointer to raw data gives us the pointer to the RSDS debug directory, and then into the first field, into RSDS, we are going to memcopy RSDS for 4 bytes. In the GUID, I think I'm just going to pick one for now. Sure, PDB GUID is 1337, 1337, 1337, 1337, OX13, OX37, OX113, OX37, OX13, OX37. Oh, I think one more time, OX13, OX37. Very beautifully. And then the H is 1. This is not an incrementally linked PDB. And finally, the PDB path. We are going to memcopy in the path. So this guy right here. For the size of this. So now the final thing we have to do is we have to link this up to the optional header. So sort of exactly what we have done with the import section right here. But this time only the debug directory entry counts and not the RSDS debug data thing they talked about. And so the virtual address is this debug data relative virtual address. And the size is just the size of this debug directory entry. Now 1 is wrong. We need to figure out which entry this is, and maybe it tells me right here. It doesn't. So let's dump in, what do we have? Dump in test.exe. No, that doesn't have a PDB. So, linker. Makes sense. Dump in linker.pdb headers. There we can see this has a RSDS section, and the debug directory is 0, 1, 2, 3, 4, 5, 6. Okay, now, first off, we have to fix up all of the compilation errors. So size of data, not size of raw data. GUID is undeclared. Makes sense. It's just declared in line. So GUID, for everyone who doesn't know, is just a, I think, globally unique identifier. And it's just 16 more or less random bytes, which usually you generate by calling a Windows function to give you like random data, but because it's 16 bytes, random data is unique, is the theory. But the way these GUIDs look is you have, I think, data 1, then 216, data 2, data 3, and then U8 data 4 is 8 bytes long. And here we need to do struct GUID now. Memcopy undeclared. Oh, memp is undeclared. Okay. Now, if we link the broke game, we should now have this RSDS debug entry. Oh, not imports, headers. And we can see this is looking fine. We have a debug directory entry. Format is RSDS. Our grid isn't looking exactly how I would expect it, but the link is correct. So let's investigate why the grid isn't looking exactly like I expected. In the linker, grid, one, 3, 3, 7, that's looking fine. 1, 3, 3, 7, 1, 3, 3, 7, 1, 3, 3, 7. It's this one. Then 1, 3, 3, 7, 1, 3. Oh, there's just a 7 missing. Okay, but I don't care to retry that. That's probably fine. So we now have half of what I wanted to do today done, namely this RSDS debug entry, and we can care about the PDB. So in write PDB, currently I only have 4 empty streams that I write to it, but now I also want to fill in the PDB information stream. And so in my documentation here, I will go into the, not the MSF file stuff, but a PDB format, and at fixed index 1, which I think for us will be 0, there's the PDB information stream. Okay, and so the way I will do this is I will write this out in the end, and here I will just have a memory arena for each. So memory arena, so linear allocators. Let's call it PDB information stream is, I don't know if I can zero initialize these. Let's look into memory arena. At least as a create, so let's say create memory arena. We are just going to reserve, like, I don't know, did I have gigabytes somewhere? Sure. You come with me. Let's just say 8 gigabytes. It's the maximum. Okay. Way too much, but it's fine. And so the PDB information stream, similar to the RSDS section, starts out with a header. So let's copy this. And push it onto the PDB information stream. Push struct, which means I might also have to copy those defines. This is one of the things that kind of annoying about even my version of C, that macros don't work. Macros don't share between compilation units. But anyway, struct. I want this guy. Okay, and then let's fill this in. The version, it tells me the current version is this guy right here from the year 2000. The timestamp is done by calling time. And if this somehow, for some reason, would need to match the other guy, I guess we just hope that in between those two calls to time, there are no second passes. The age is 1. Again, this will not be an incremental PDB. And then the grid, linker grid, probably have to copy as well. Come with me, little fellow. And this guy as well. So then after the PDB stream header is a serialized hash table. In this hash table defines so-called named streams. Later on, we will care about one named stream, namely the /name stream, which is a global string pool. But for now, I don't think we need this global string. We don't need this string table, so I'm just going to set everything to 0. So U32 string buffer size is push struct into the PDB information stream of the U32, and then we set that to 0. Which means the string buffer right here is empty. Then we have the amount of entries and the capacity. And this already 0 initializes, so I guess I could also leave this one out and just say something like string buffer size then we have something similar for the amount of entries, the capacity, and then there are these bit arrays. These have a word count and then that many words. So this is present bits word count and deleted bits. All of these are 0. Let's say node. Now the main stream table is empty. Then the entries are for amount of entries, which we have set to 0. Finally, there's the last U32, which is unused. Okay, so much for that. Here's some stuff to recreate it. Here's a hash function for this, which we all have to care about later when we actually fill this in. Maybe at least, maybe I'm just going to hard code it. And then finally, the unused value, yeah, okay, so it comes from that. After the named stream table, the rest of the PDB streamed is used for a set of feature codes. The following feature codes are defined. So the imp VC110 is this, imp VC 140, which I think is the one that we cared about So do I still have that in my history? Probably not. So in the PDB, we had the PDB validate.exe on the minimal one. And then I would like to dump that. We can see here it has one feature flag, namely this from 2014. Okay. In the right PDB code, I am going to push this. And I'm going to do it like this. So pushing it immediately, writing it in and saying feature code is this. Okay, and then to write out this PDB information stream, I have to initialize this stream. And here, I'm pretty sure I have to use stream 0 instead of stream 1. But let's check that and write MSF. Have information for this. Does still print some random shit. Okay. Yeah, amount of streams +1. Yeah, so it expects that the amount of streams is one less. So here I use stream 0 for data. Is the base of the PDB information. So how I'm going to do this is, oh, maybe I can just go into the memory arena. So .data or .base. So if you look at memory arena, it has this base member. Then the size is arena current of the stream minus the base. And then an offset we don't need to define. And then if we write that, we should, in theory, have a valid PDB. Time undeclared. I was not undeclared in the other one. That's some weird. Might be some weird define that they have in the header files. Anyway, we compiled the linker. Now we want to relink broke. So and in theory, if we do cv dump a.pdb, doesn't tell me much. And I guess /pdb/validate.exe a.pdb. That thinks it's fine. To maybe see if remedy, so remedy might just crash because it's a very empty file, but we will see. Remedy bg a.exe. Let's see if the debugger can load my PDB and what it might think about it. And so I have to start at entry point. Didn't crash or anything. And tells me all the symbols are out of sync. That's what it tells me. But it told me it could load it. I wonder why it's complaining about the symbols being out of sync. Let's, well, dump what it tells me. We can see my dump path thinks this is the PDB information size, the PDB information, and then dump bin slash headers a.exe. And then the linker, no, wait. What I produced is this. So let's see if these are the same, and if so, I think I am satisfied for today. Yeah, even the timestamp is the same. So I'm not sure why Remedy would complain about it being out of sync. But we have a very bare bones PDB working. We have the RSDS format working to link to the PDB. So from now on, each time we implement something new in the PDB, we can check if it worked by checking what the debugger says about it. So I will do that in future videos, I think. So thank you for watching. If you enjoyed this, maybe see you again.